Hello. Welcome to Breaking the JavaScript Speed Barrier with V8. My name is Daniel Clifford. I'm the tech lead and manager of the V8 team. If you'd like to follow along in the slides, there's a link here on the first slide. It might help for you in the back rows to read the smaller fonts in some of the code slides later. I'd like to talk to you today about optimizing the performance of your web application. Now, this can mean a lot of different things to a lot of different people. This could mean optimizing your WebGL code to get more frames per second in a game. This could mean reducing the number of network round trips in a client-server application. But what I'd like to talk to you about today is raw JavaScript execution performance with V8, the JavaScript engine inside of Chrome. The V8 project has recently moved to the development center, the Google Development Center in Munich, Germany. And as you may know, Germany is the home of the Autobahn. And what you may not know is the Autobahn is not actually a single stretch of road from Hamburg to Munich that runs straight through the middle of the country, but rather it's a network of roads. And these days, most of the Autobahn actually has a speed limit, but there are still a few stretches of the road that don't have any speed limit whatsoever. And you can go as fast as you want, as fast as you can. And so as a resident of Munich and a resident of Germany, I feel especially qualified to speak about moving at speeds that would get you ticketed here in the United States. You might ask the question, who cares about performance? JavaScript performance is fast enough. This is something that only game developers need to worry about, or the developers of highly interactive applications. But I'm here to tell you that you should care about performance. Everybody who develops a web application should care about performance. And the reason is that JavaScript performance matters. It still matters. It's not just about making your current application run faster. It's about enabling things that you have never been able to do in the past. Every cycle that you win back when you do performance optimization, you can invest in something new that you haven't been able to do before. An interesting comment about these pictures, they were taken on the same street, only a few feet away. I think it's interesting that in the same place, giving a slightly different perspective, you can have a completely different view of the world. So let's talk about breaking the speed limit today. I'd like to use a checklist as the basis of how you optimize your web application. It's a relatively straightforward model, but it's very powerful. And the first step of the checklist is to make sure you are prepared before you have a problem. This is the piece that is the most expensive. This is the one that takes the most amount of time, and I'll be spending the most amount of time talking about it today. But this is the one that you have to do to make the second two steps possible at all. The second step is to identify and understand the crux of your problem. And if you know how a system works, if you're prepared before you go into the second step, it makes it much easier to find your problem. The third step, you fix what matters. And hopefully, this is the step that's actually really easy after you've done the first two. Now, this is a relatively simple model, but like I said, it's very powerful, and you can even apply it to real-world situations. So I'd like to tell you a story about using the checklist. And I like to do recreational mountain climbing. I'm not very good at it, but I have a friend who is very good at it, Michael Stanton, and he's taught me everything I know about mountain climbing. And I trust him on the mountain. I trust him with my life. And that's how we found ourselves in the summer of 2010 up here. And it was a beautiful day. We'd been on the mountain all day. We hadn't seen another soul. We had the whole mountain to ourselves. And we were 2 rope lengths from the top, from the summit. We were almost there. And I was belaying Michael. I was making sure that if he were to fall, that I would catch him. And he was leading ahead. And he climbed ahead of me around a corner, out of sight. And I heard him struggling with a particularly tricky climbing problem. Then I heard 2 sounds that I will never forget in my life. And the first one was the percussive sound of a rock coming loose. And the second sound was the sickening thud of that rock hitting Michael. He fell. I called his name. But all I heard was silence. I realized in that moment that I had a performance problem. And The checklist that I just presented to you would be the key for me to get out of that situation. I had to be prepared before I ever got on that mountain. I had to make sure to identify the problem that I had in that very moment, the key problem, so that I could fix it quickly. Somebody's life could depend on it. Now, I hope you never are in a situation like that your life depends on applying the checklist. So why don't we go to an example which talks about a less life-threatening performance problem. Let's talk about JavaScript. So I have put together a sample problem that I'd like to talk about throughout the course of this talk. And it is a toy problem that I've come up with, but I think it's representative of some of the things that, some of the performance problems that you might face in your own code. And the problem is to compute the 25,000th prime. Pretty simple algorithm here. You start at 1, you count up, and you take each candidate number, and you look in a list of primes that you're maintaining and see if any of those primes can be divided into that candidate number. And if it can, then the candidate number is not a prime. If none of the prime numbers go into that candidate number, then we have a new prime, and we add it to the list. And I wrote some code in C++ and in JavaScript. Don't sweat the details of this code. I just wanted to show you that it's about the same amount of code, and I tried to do a pretty good job of porting the code from JavaScript to C++, so it does the same thing. And then what I did is I actually ran the code. I compiled the C++ code with GCC and ran it, and you could see it took about 3 seconds to compute the 25,000th prime. Then I took the JavaScript code, and I didn't run it in the browser. What I did is I took the debugging shell that's available as part of the V8 open source code project, and I compiled that and ran the JavaScript with the debugging shell. The debugging shell makes it possible for you to concentrate on JavaScript-specific problems. So for this presentation, I'll refer to the debugging shell in most of my examples. You'll see that when I ran the prime code in JavaScript, it took 15 seconds. So JavaScript's about 5 times slower than C++, right? That's not so bad, right? Of course it is. Yeah? So I just made a big mistake. I've told you about this checklist, and I just completely ignored it. I was not prepared. I don't have enough information to make judgment about whether my code is bad or good, whether that number is something I should expect or not. I didn't even try to analyze any potential performance problem. And I didn't even get anywhere close to fixing any problem. I'd like to show you how V8 has improved since Chrome came out. This is V8 score on the V8 benchmark, version 7. And you can see that it's gotten a lot better since we launched Chrome. And we're now at the position with V8 that we can actually make a comparison against the performance of C and C++ code. You can expect to be in the ballpark for certain code. So don't give up here. When you're in the same situation where you see, we're slower than C++, or I'm slower where I want to be, don't just give up. Apply the checklist that I presented to you and see how far you can get. Demand that your application is faster. So how much faster do you think we can get the JavaScript code to run? Who here thinks we can do it? We can get it 3.5 times faster. All right, we got maybe 5, 10 people. 35 times? Takers? OK, also a couple of people. I know, you know how this game works. 350 times. One person. The V8 PM. So 3,500. All right, we got to get at least one brave taker here. So I think the most votes were for 35 times. Let's apply the checklist and see how far we can get. Now, I told you the first step was to be prepared. And this means we're going to dive into some technical details of V8 so that you can understand how it works. So fasten your seatbelts. This is where things get a little bit racy. So what does prepared mean for V8? I mentioned this before. You need to understand how V8 optimizes your JavaScript code, you need to understand how V8 actually works so that you can help it optimize your code. Because once you understand how V8 works, then when you actually write your JavaScript code, you can keep those things in mind and make sure that you don't make some of the mistakes that will fool V8. Make sure you learn the tools that are available to you. There's some great tools in Chrome, the dev tools, and V8 has some built-in tools in the debugging shell that can really help you understand what's going on in your JavaScript and help you make it better. All right, so the first thing I'd like to talk to you about is hidden classes. So JavaScript doesn't have explicit types, and this presents a bit of a challenge to a language implementer because type information is very valuable in specializing generated code to be very efficient. And if you don't have that type information, it makes it much more difficult. And it's hard to gather this information efficiently and quickly when you're compiling JavaScript code because compilation is part of the execution time of a JavaScript program. Every cycle that you spend compiling a JavaScript script before you execute it is a cycle longer that it takes to actually get to doing the work. So we have to find a way to get executing code as fast as possible. And it makes it difficult to do expensive reasoning about types at compilation time. And that makes it extremely difficult to get it close to the performance of C++. However, there are some tricks. Hidden classes help make V8 run JavaScript faster. V8 internally creates hidden classes for objects at runtime, not at compile time. And that's how we get around the problem of compiling upfront, getting the information upfront, because we gather the hidden class information as we go. And here's a key insight, and this is one that we'll repeat throughout the presentation. Objects with the same hidden class can use the same optimized generated code. And that means if you help teach V8 through the way that you structure your code, which object has the same hidden class, you can help it to generate optimized code for those cases. I'd like to show you how this works in a very simple example. So I've got a constructor function here for an object point, and I'm going to instantiate it twice. And let's see actually what V8 does behind the scenes. So the first time the constructor gets called, V8 creates a new hidden class. So what you see here is on the right-hand side is you see the new point object. The first entry in the point object is a hidden class to an empty point hidden class. And as we assign to the members in point, what V8 does is actually realizes, you're changing the hidden class by adding a member to it. And we create a new hidden class, and the point object gets assigned to this new hidden class. And if we add another member, in this case y, we get yet another hidden class. And you see what happens here is that not only does V8 create new hidden classes as new members are added, but it keeps track of what had to happen to get from one hidden class to another one. Yeah, so you see we went from an empty point object to a point object with an x to a point object with an x and a y. And that's important because the second time that we call the point constructor, this hidden class structure is already there. And as the code is executed to add the members x and the members y, you'll see that the object also gets new hidden classes, but it gets the same hidden classes that we created the first time through. So that at the end, we actually have P1 and P2 having the same hidden class. The problem is that if we add a member to P2 that we haven't added to P1 after the fact, outside of the constructor, what happens is that we create yet another hidden class for P2, and it is different from the class for P1. So we're not able to use the same optimized code for both of those objects. So be aware that by doing something like this and creating hidden classes, you're defeating some of the optimizations that V8 can do. I'd like to talk about speed traps to avoid in this presentation. For the most part, all of the advice I'm going to give you today is something that is eternal. You can assume that the tips that I give you today you can use forever, except for a couple of cases where I'll say this is something that's temporary, something that we're working on and we're trying to make better. So let's get to the first speed trap. which is make sure to initialize all members in your constructor functions. This comes from the example I just showed you, which is you need to teach V8 which hidden class objects should have after they're constructed. And the way to do that is by putting all of the member initialization in the constructor. Always initialize object members in the same order. This follows from that example that I gave you. If you add members in different orders, you create a different tree of hidden classes. And at the end, you'll have objects with two different hidden classes that can't use the same optimized code. Next thing I'd like to talk about are numbers. So because we don't have a lot of type information in JavaScript, we have this dilemma. We want to be able to generate code that can handle all possible different values, all different possible types. But you want to be able to have an efficient representation of numbers. And how do we do this? Well, we use a technique called tagging. So inside of V8, we pass around values as 32-bit numbers and objects, but we want to be able to use the same 32 bits to represent both. And that way, we can have one code path that can handle, in many cases, the objects and integers. Yeah? So what we do is we use the bottom bit in each of the values to have a special meaning. If the bit is set, it's an object pointer. If it's clear, it's what we call a small integer, or a SMI. And that's a 31-bit signed integer. Now, if you have a numeric value that you're passing around, assigning to a member, that is bigger, it's a numeric value that's bigger than 31 signed bits, then it doesn't fit in one of these SMIs. And we have to create what's called a box for it. We box the number, we turn it into a double, and we create a new object to put that number inside of it. And what follows from that is the next speed trap to avoid, which is make sure, whenever possible, you use 31-bit signed numbers for performance-critical calculations. Because if you exceed 31 signed bits, we will have to convert it to a double value. Now, there's some optimizations that we have that doesn't make it as bad as it seems, but there are cases where that process causes an allocation, and that means that some mathematical operations can cause allocation. The next thing I'd like to talk about is arrays. This brings some of the elements together of the previous two sections. In JavaScript, you can have very large arrays, and you can have arrays that are sparse, that don't have every element inside of them. Yeah? And so V8 actually has two different methods to handle two different types of arrays. The first one is fast elements. And fast elements, they have a linear storage buffer, and V8 uses them if the set of keys for the array is very compact. If that's not the case, so you have a very sparse array, then it uses a different format, which is dictionary elements. Fast elements, linear buffer, very fast and efficient to access. Dictionary elements, it's a hash table, much more compact, but also more expensive at runtime to access. Kind of obvious here. If you want to have your arrays be very fast, make sure that V8 uses fast elements to represent them. And the way to do this is to make sure that your keys start at 0 and that they're contiguous. Yeah. So don't create an array and start using index number 25,000. Yeah. Start at 0 and go up. Also, don't allocate really large arrays that you're not going to use everything in. Right? So if you allocate an array with 65,000 elements and you only use the first 5, V8 thinks, well, that's a very sparse array. Yeah? And we'll switch it to dictionary mode, which means the access of the elements will be slower. Don't delete elements inside of arrays. Same principle here. Because when you delete elements, it makes the key set sparse, and it can lead to V8 switching the elements to dictionary mode. Don't load from uninitialized or deleted elements. This is an important one. It's easy to get wrong. Here's an example. Your code will work. You won't notice, and it won't make a difference in the output. However, it will make things a lot slower. So here's an example of doing exactly this. I have a loop here that accesses an array, and it uses the or equals operator, which means it takes the existing value in the array, ORs it with something, and then writes it back. But the first time that you do that, you're accessing an empty array. And when you do that, the JavaScript spec says that's an undefined value. But that's OK. It can be converted to 0, and it's exactly what it does here. It converts that to 0 to do the OR equals, and then stores it back in. But that process of conversion means that this operation has to do more checking, and it's more expensive. And by simply initializing the value before you use it, that's the second example here, you can make your code, in this case, about twice as fast. So what about arrays of doubles? Remember, I talked about tagging, that we have to wrap double numbers inside of special objects. So if you have an array of them, doesn't that make it expensive? Because each element has to have this wrapper object to store the double value. Well, there's a trick that we can use there too as well. So we have a mechanism called unboxing. When you unbox a double, you take the 64-bit IEEE number inside of this double object, and you take it out, and you put it into a linear buffer. So what we can do is track in the hidden class of an array the types of elements that are contained in the array. And if the array contains only double values, it becomes unboxed. And what that means is that it takes all of those numbers out of the heap objects, out of the wrapper objects, and lays them out in a linear buffer of doubles. But again, it's only if there are double numbers inside of the array. This causes a hidden class change. Generally, that's good, because if you convert the double numbers into a flat buffer, if you have an array of doubles and it's in a flat representation, it's very efficient to access that. And when you store into it, it doesn't require any allocation. But you must be aware that converting between the array that's boxed and unboxed has a cost, and it changes the hidden class. And careless manipulation of arrays can lead to a lot of extra work through this boxing and unboxing. I'll give you an example of that. Here's a pretty simple snippet of code. I create a new array, and I assign a bunch of values to the first couple of elements. Looks like there's not a whole lot of work to do here. But because I created an empty array, the initial object that I have, you'll see, doesn't actually have any elements at all, because it's empty. So the hidden class says, hey, I'm an array, and I'm optimistically going to assume that I'm only going to assume it contains SMI values, and that I'm not going to have any deletes, no holes. We could do that because the array is empty, so it's actually a true statement. It only has SMIs because it has nothing in it. What happens when we assign to the first element of the array, because we didn't have a backing store for the elements yet, we have to allocate it. And by default, we allocate a buffer that has room for 4 elements. Now that the backing store is actually there, we can store the first element in here. And again, this is stored as a SMI, as one of these compact 31-bit signed integers. And now that we have space, we can also assign the second element, also not a problem. However, the next assignment assigns a double value. And what this does is forces V8 to convert the format of the backing store, because we can't store a double array directly in a double value directly into the array. But what we could do is we could convert the existing integer values to doubles, and then with the unboxed version of this array, we could store the 0.5 value. And that's exactly what V8 does. It reallocates a new buffer. This time, each of the element slots is 64 bits. It converts the existing small integers into double values, and then it assigns the 0.5 to the third element. You'll also notice that a hidden class change happened here, because what we did is added a double value. So it's no longer true that the array only has SMIs. We now have doubles in there. That means that the hidden class has to be changed. It causes a hidden class change. Something similar happens when we try to assign true. So true, there are certain objects in JavaScript which are kind of oddballs. We actually call them oddballs. True, undefined, null. They are not really objects, but they kind of act like objects, but they're certainly not numbers. So when I assign true to the third element, or the fourth element here, it causes another allocation, because we can no longer represent this new value in this unboxed double array. So we have to convert it back into its tagged format, which means converting the elements that can be represented as SMIs back into SMIs. It means reboxing the double value. And now we have a backing store that we can actually store the true value in. That's a lot of work. This is a very short piece of code, but we did 4 allocations, 2 array two hidden class changes for just a couple lines of code. There is a better way. If you use an array literal, this is a hint to V8 up front what the values are going to be inside of the array. And given this example here, we have a single allocation. All of this can be done in one allocation. The correct backing store format can be selected at compile time. And we don't have all of these conversions in the initialization of the array. So, touched on this already. Speed trap. Make sure, wherever possible, you initialize arrays with array literals, especially for fixed size small arrays. Also for small arrays, make sure to pre-allocate them before you use them. Now, again, this is different than large arrays. Large arrays, remember, more than 65,000 elements. You want to make sure to grow as you go so that you don't go into dictionary mode. For small arrays, even if they're not completely filled, even if they're small, if they're sparse, if they're small, V8 will use fast elements for them. But only if you allocate the correct size will you be able to avoid allocations when you go from an empty array and store the first element into it. Don't store non-numeric values in numeric arrays. So if you have an array of double values, V8 can generate very good code for manipulating those values, for those double values. But if you put an object into the array, we have to box everything again, and the code that we generate is a lot less efficient. OK, we've talked about hidden classes and how they are an important piece of optimizing code. Let's actually talk about how we generate code in V8. And this will maybe help you understand a little bit better why it's important to make sure that you understand the hidden classes. So a V8 has two compilers. The first one is called the full compiler because it can actually implement the full set of JavaScript features. It generates good code, but not great code. There's an optimizing compiler, which I'll talk about later, which produces much better code for most of the language. The goal of the full compiler is to generate code quickly. I talked about before the fact that any time you spend compiling code is added to your execution time. So the full compiler's strategy is to get executing code as quickly as possible. It generates code that is just good enough. But because of that, it basically doesn't do any type analysis. It doesn't know anything about types. And the way that it solves the problem of implementing operations on different types efficiently is a technique called inline caching, or inline caches. And what inline caches do is they gather type information at runtime, and they optimize the code as you go. So you pay as you go. And here's the way inline caches work. An inline cache, or an IC, is a type-dependent small chunk of code that knows how to do an operation given specific hidden class inputs of a particular hidden class. And what they do is they validate the type assumptions. They get a couple arguments in. They check to see if the hidden classes are as they expect. And if they are, then they know that the code that is in the IC is the optimal code for implementing that operation. If not, something has to happen. A new IC has to be generated that can handle the new type information. And at runtime, if different types are seen than what are expected, then through backpatching, the code is changed to use new specialized code for the new types that are seen. I'll give you an example of how that works. Here's a fragment from the code example at the beginning, the prime number generator. I'd like to take a particular fragment of code there, which takes an element from the primes array and checks whether the candidate number is divisible by that number. And let's see what the full code generator does with this code. Now, don't sweat the details. I'm going to show some assembly language here. And it's not actually important what the details are here, but I want to show the pattern of what actually goes on here. So each expression generates a little chunk of code here. You'll see that there's some preparation code, and then there's a call out, a call to an IC to actually do the work. Likewise, for the array element access, there's some preparation work, and then a call out to the IC to do the work. And for the mod, the same thing. And the thing to notice here is that initially, the call is to this initialize version of the IC, because we don't know what the types are going to be. We'll only know that at runtime. And this is how it works at runtime. The code on the left here is a small, almost impossible to read version of the code I just showed you. And when we're executing this code for the first time, and we get to this IC, the first IC, it calls an internal routine that initializes the IC. It looks at what the arguments are to that operation the first time. It checks the hidden classes. And it says, oh, I know how to do that. I can generate specialized code for that. It does so. And it backpatches the address so that the next time you come through the code, it does the same thing again, assuming that the next time you run, you're going to have the same hidden classes, the same types of objects, which is an optimistic but usually valid assumption. It does the same thing for the access of the array element and for the mod operation. And you'll see that each of the ICs, all they are is specialized code that know how to do the specific operation for a given set of object types that are input. This makes a big difference in performance. And this is why you need to understand how some of this stuff works with hidden classes. Because if you get it wrong, you don't actually get the performance improvement that you will see or should see when using ICs and then later the optimizing compiler. So if you're running the sample code that I showed at the beginning to generate primes without ICs, you get an execution time that's over 600 seconds. When you turn ICs on, don't have the optimizing compiler on yet, it makes a big difference. Right? So this is about a 20 times speed improvement. Now, I'd like to introduce a concept that we'll also come back to later. Monomorphic better than polymorphic. Sounds pretty complicated. It isn't really. Monomorphic operations are operations that always work on objects with the same hidden classes. Right? So the first time you execute an IC, we look at the argument types for the operation, we look at the hidden classes, and we remember them. And if the next time through those hidden classes are the same, it's monomorphic. And if the next time they're the same, it's still monomorphic, and it stays that way. If at any time we see different hidden classes for the arguments to an operation, then it becomes polymorphic. And it turns out that monomorphic operations are easier to optimize, or the code that we generate is better than for polymorphic operations. So here's an example. Let's say we have a function add that adds two things. And if I call that with two integer arguments, it's monomorphic. However, if I call it again with two string arguments, I use the same operation, this plus operation, to work both on integers and on strings. And at that moment, it becomes polymorphic. And it becomes more difficult for V8 to generate good, really efficient code for that plus operation. So the speed trap to avoid here is wherever possible, don't try to mix operations or objects of different types in specific operations at a particular place in your code. Prefer monomorphic code to polymorphic code wherever you can. I'd like to talk about the optimizing compiler. We talked about the full compiler generates pretty good code, gets executing as fast as possible. The optimizing compiler comes back later for the code that's really hot and recompiles the hot functions. Why does it do this? Well, we've gathered information about the types of the objects that we're operating on through the ICs. And the optimizing compiler can take that information and make decisions about how to optimize the code better. What happens is the optimizing compiler takes that type of information from the ICs, and it speculatively inlines a version of the operation based on history, what it's seen before in the ICs. And it also means that it can inline function calls that are monomorphic. This includes constructors. This is actually a new feature that we've added recently. By enabling inlining, by inlining this operation in the optimized code, other optimizations become possible, and that's what the optimizing compiler will actually do. We'll go over this inline code and find more opportunities to make it faster. Let's see how that works. Again, a warning, here's assembly code. It's a very similar process to the full code generator. We generate a little piece of code for each of the expressions. But this time, you'll notice, as we generate each piece of code, there's no call at the end. And in fact, when we're done, it's straight line code. So let's compare the performance using the optimizing compiler with the 2 runs that we did before, you'll see that with the optimizing compiler, we're even faster. We're about 50 times faster than the original code. One thing that's really useful is actually to find out which functions are being optimized by the optimizing compiler in V8. So there's an option you can pass to the D8 shell. That'll do just that. It'll output the information about which functions get optimized. However, there are certain circumstances in which the optimizing compiler can't optimize a function. This is called bailing out, or that's what we call it, bailing out. And the reason is there are certain language features that are just not supported yet by the optimizing compiler. The most obvious example is try-catch. So if you have a function that contains a try-catch block, the optimizing compiler right now can't optimize that. We hope to change that in the future. But until then, there's a workaround. If you have performance-sensitive code that you'd like to call from or access from a try-catch block, wrap it in its own function. Here's an example. We have a function that's performance-sensitive. We call that from the try piece of a try-catch block in another function. And by doing that, it allows the optimizing compiler to optimize the performance-sensitive function, even though it can't optimize the try-catch block. If you want to find out which routines cannot be optimized by the optimizing compiler and why, there's an option you can pass to the debugging shell called trace bailout, and that'll actually tell you the functions that could not be compiled and why. The last thing I'd like to talk about is de-optimization. So the optimizing compiler is pretty good at generating code, but there's a catch. The optimizations that it does are speculative. It makes the optimistic assumption that what it has seen in the past is going to be just like what it's going to see in the future. And that usually pays off, because usually your code keeps running like it has before. However, as with all optimistic assumptions, that may not be the case. So when you're driving down the Autobahn in Germany and you're doing 200 kilometers an hour, sometimes you're working under the optimistic assumption that you're not going to be caught going over the speed limit. Remember, I told you there are some stretches of the Autobahn with the speed limit. And you'll see out of the corner of your eye a red flash from 2 of these things on the side of the road. And you've just been caught in a speed trap, because your optimistic assumption that you were not going to be caught speeding was wrong. And what do? You slam on the brakes, you slow down to the speed limit, and you probably drive that way for a while. Yeah, slower. There's a similar process that happens in optimized code in V8. Invalid assumptions lead to de-optimization. When one of the assumptions is no longer true, when one of the hidden classes that you get for an argument to an operation is not what you expected, then the specialized code we generated is no longer valid, and we have to de-optimize. What does that mean? That means we throw away the optimized code because we know the assumptions we made are just simply no longer valid. We resume execution in the right place in the full compiler code, so we can continue execution, but now it's at a slower speed because we're using the version of the code that is good but not great. And a re-optimization of the function might happen later because we're going to continue to gather type information in the ICs in the full compiler code. But for the short term, you're going to run more slowly. And what that means is that de-optimization is something you want to avoid. And one way to do that is to make sure that you don't introduce hidden class changes at a late time running your code. Right? If you have types, object types that you run in optimized code, and V8 chooses to optimize that code, and then you later introduce new types, that optimized code will de-optimize. And if you do that too often, it has a cost. You can tell the debugging shell to output the routines, the functions that it de-optimizes on by passing the trace de-opt option to the debug shell. And it'll output which ones it de-optimized on and why. Now, most of you are doing web development, I assume, and therefore you probably want to be able to look at your code in Chrome as well as directly in the D8 shell. You can pass these options that I've mentioned also directly to Chrome using the JS flags option, and the output will all show up in standard out when running Chrome. OK, so that was the be prepared part. You now understand a little bit about how V8 works. Let's talk now about identifying and understanding problems using that knowledge. What does that mean for V8? First of all, ensure the problem that you're looking at is a JavaScript problem. And this is sometimes a little bit tricky. You could use the dev tools in Chrome to figure out where you're spending time in your web application. It may look like JavaScript, but be careful. It might be the case that there's also DOM interaction. So a really good way to do that is if you can take that code that you think is the performance bottleneck, pull it out, and run it in the D8 shell. That means it's pure JavaScript, because the V8 project is just JavaScript. It doesn't have, it's integrated into Chrome, but in itself, it is just the JavaScript execution environment. So if you can take that code and run it with the D8 shell, then you can analyze the problem as a JavaScript-only performance problem. Collect metrics, measure where you're spending the time in the code, and then locate the bottlenecks and fix them. So remember the example that we had at the beginning, the prime number generator. If you run it in the shell and pass an additional argument, the --prof argument, it will run the program while also sampling the execution profile. And it'll write a log that you can then analyze with another tool to see where you're spending your time. Before we look at that output, where we're spending the time, I'd like to go over briefly again where we're spending the time, or what we're doing in the program. There's a couple important functions here in the prime generator. First, we add a prime. There's a function to add a prime to the existing list. There's a function that actually tests whether candidate number is divisible or is divisible by one of the existing primes. And then there's the main routine, which does the high-level algorithm. It starts at 1, goes up, checks that number, whether it's divisible by an existing prime. If not, it adds it to the prime list. Otherwise, it goes to the next number. So what's our expectation? The prediction is that we're going to spend most of the time in main. And the reason for that is all properties and functions are monomorphic. I wrote the code to be that way. All numeric operations are SMIs. We do a pretty good job at optimizing those. All the functions could be inlined. And there are no de-optimizations or bail now. So my expectation is V8 is going to do a really good job of optimizing this code. OK, so let's take a look at the output and see where we were spending our time. So this is the output of the tick processor. It takes this output log that's written with performance data, and it prints it in a pretty format. You'll see there's 2 sections of the output here. I've actually abridged this. It's much longer. But these are the important parts for our profile here. There's a JavaScript section. This is the time we're spending in generated code. This is JavaScript code executing in either the full compiler code or optimized code. And then there's a C++ section, which is it's often the case that you'll have C++ symbols in the profile because there's some operations that we can't do in generated code, so we have to call out. And as expected, we spend a lot of time in main. But it's actually about 25%. You'll see there's 3 columns here. You see how many ticks you're spending in in that routine, in this function. And you'll see what the percentage is of the overall execution time. But in this case, it's only 25%. That's weird, because I expected a lot more. V8 should do a really good job on this code. If you look at the other items that show up in this profile, this is weird. We're spending time doing a binary op stub with an oddball. An oddball, remember I told you those are things like true and undefined and null? We don't have that in our code. That's kind of strange. And we're spending a lot of time in library code doing modulo, and that's kind of strange. We should be able to inline that as well. I didn't expect that. And then here's another one that's kind of weird. We're doing a conversion from a number, extracting, or taking a number and boxing it. And we really should be generating very good code for this program. We're spending way too much time doing something that's not executing the JavaScript. We're calling out to libraries. Something is very wrong with this code. So can you spot the bug? The hint is that our array is only of length prime count, and we've actually exceeded the end of the array in our calculations. And in both the C++ and JavaScript version, it doesn't make a difference in the results. And this is the thing that you've got to watch out for, is that even though you don't see that there's a problem in the results, the program's a lot slower than it needs to be. So let's fix that. Let's actually not do an out-of-bounds array access. And we'll rerun the profile with the fix. And you'll see this time, this is what we were expecting. That small change now makes us generate much better code because we're not accessing outside of the array, getting an undefined object, this oddball that we're trying to do math on. And now we're spending over 99% of our time in main. This is what we expected. So let's see actually what this makes, how big of a difference this makes on the profile. And when we run the code against the C++ code again, look at that. C++ code, 3 seconds. JavaScript, 1.8 seconds. We're 60% faster. Wow. I forgot to optimize the C++ code. So when you do that, C++ is still faster, but it's 17% faster. It's ballpark. Have to take all of this with a grain of salt. I chose an example where I knew V8 would do a pretty darn good job. More and more, we're optimizing more cases that makes V8 faster in more situations. So I expect in the future we'll get closer and closer. But my point here is that you need to make sure to take a look at, to spend the time optimizing your code, to know where you're spending your time, because you can actually make your code very fast. So fix what matters. We did a lot of time analyzing our existing profile, tweaking it, knowing how V8 works. The last thing I'd like to point out is make sure you don't forget to optimize your algorithm. So I have a new version of the program here where instead of iterating over all the prime numbers, I only iterate to the square root of the candidate, which is sufficient to actually test for whether it can be divided by one of the prime numbers. And if I run that result, if I run that in the time that, then you'll see that now I'm under 0.05 of a second. And if we compare that with the original version, which was 15 seconds, it's a 350 time speed up. So, in summary, keep your eyes on the road. Be prepared. Learn a little bit about how V8 works. Identify and understand the crux of your problem. And fix the thing that matters. You don't have a whole lot of time to do performance optimization. Make sure that every minute counts. And my friend Michael is fine. He had taught me how to tie a special knot, which freed my hands while he was hanging. I was able to call on my cell phone the mountain rescue. Michael regained consciousness, and I could lower him down. The helicopter came and took us off the mountain. So even though he had a couple broken ribs, he's fine. Thank you.